Hi everyone, this is the last video for chapter 3. We're going to start with the propagation of uncertainty. It's section 3.4. Let's get started. Before we learn how to propagate uncertainties, we have to understand the difference between absolute and relative uncertainty. So absolute uncertainty gives margin of uncertainty associated with a measurement. So for example, you're reading a burette and it's plus or minus 0.02 mils. We say that plus or minus 0.02 is the absolute uncertainty associated with that reading. The relative uncertainty compares the size of absolute uncertainty to size of measurement. All that really means is you're dividing the uncertainty by the magnitude of the measurement. So for example, your reading in the calibrated burette is 12.35 plus or minus 0.02. So the relative uncertainty of that would be 0.02 divided by the magnitude of that measurement, which is 12.35. If the relative uncertainty is the absolute uncertainty divided by the magnitude of the measurement, then the percent relative uncertainty is just that answer that you got times 100 to make it into a percent. Most of the time, the problem is going to give you the absolute uncertainty. What you will have to find is the relative uncertainty, and they might also ask you, what is the percent relative uncertainty? So you just multiply the number that you got for the relative times 100. All right, let's move on. Now we can start talking about the propagation of uncertainty. Remember, every measurement you do has an uncertainty associated with it. So it's really important that we know how to deal with these uncertainties when we have different types of measurements. We can usually estimate or measure the random error associated with a measurement, but if possible, uncertainty is expressed as the standard deviation or as a confidence interval. Now, we're going to talk about standard deviation and confidence interval in the next chapter. For right now, we're just going to learn how to propagate errors. The following discussion in the rest of the slides only applies to random error. We're actually assuming that you have identified systematic error and it's been detected and corrected. Like I alluded to before, in most experiments, actually probably all experiments, you have uncertainty that's associated with the measurements that you make. And you have to take those uncertainties and do arithmetic operations with them that are special to the specific type of math that you're doing. For example, what I mean by that is if you add or subtract, the rules are different. If you multiply and divide something, the rules are different. So it's not simply just adding the errors up and getting a total for the error. No, that's not simply how it is. So we are going to learn how to manipulate those errors in different types of calculations. The rule for the propagation of uncertainties in addition and subtraction is actually pretty easy. So let's say you had this arithmetic problem which has these three numbers. You would add the numbers like normal. So you have 1.76 plus 1.89 minus 0.59. So that gives you a total of 3.06. But then you have those uncertainties right next to those measurements. So you would take those errors and square each of them and then sum them all up. So basically the sum of the squares. And then you take the square root of that number. So if you do that, you take 0.03 squared plus 0.02 squared plus 0.02 squared, and then square root that answer, you get 0.04. It's pretty simple. So the absolute uncertainty is 0.04, and you can write the answer as 3.06 plus or minus 0.04. If the problem asked you for a percent relative uncertainty, you can do that as well. All you have to do is take the 0.04 and divide it by the magnitude of the measurement. We just learned that in the previous slide. So you can also display the answer as 3.06 plus or minus 1%. Let's do an example with the addition and subtraction. Here's the problem. The volume delivered by a burette is the difference between the final and the initial reading. If the uncertainty in each reading is plus or minus 0.02 mils, what is the uncertainty in the volume that was delivered? Okay, pretty simple. So the volume that's delivered is final minus initial. So 17.88 minus the starting, which was 0.05, is 17.83. Now, what is my uncertainty associated with that measurement? Each reading has an error of 0.02 mils. So I'm going to take 0.02 mils squared plus the error in the final reading, 0.02 mils squared, add that together, and then square root it. You'll see that you get 0.03. So your answer would be is 17.83 plus or minus 0.03 mils. The rule for multiplying and dividing is actually pretty simple as well. All you have to do is take the errors that you have and convert them first. Before you do anything, you have to convert them to percent relative uncertainties. Remember, the percent relative uncertainty is that relative uncertainty times 100. So you convert all of the errors to that first, then you square them, add them all together, and then square root them. That's how you do it. Let's do a problem to make sure we understand. Let's say we had this problem, 1.76 times 1.89 divided by 0.59. Of course, each number has an associated error with it, but if you were just to do the numbers, you would get 5.64. Now, to manipulate the errors, since you're multiplying and dividing, you have to first convert them to percent relative uncertainties. Then you can take them and square all of them, add them, and then take the square root. So if you take 1.7 squared plus 1.1 squared plus 3.4 squared and take the square root of that, you'll get 4%. So your final answer is 5.6 plus or minus 4%. If I asked you to convert it back to absolute uncertainty, that's pretty simple as well. All you do is take 4% of the answer. So you would multiply 0.04 times 5.6, and that'll give you 0.2. So your final answer in absolute uncertainty would be 5.6 plus or minus 0.2. So what if you had a problem that involved both addition and or subtraction plus multiplication and or division? The way you do that is exactly how you would do it if you didn't have any errors associated. You follow the same order of operations that you would normally. What you would do is you would take care of your addition and subtraction first, and then once you're done with that, then you multiply or divide. So that's what we're going to do here with the errors as well. So first, you have to work out the difference in the numerator, which is 1.76 minus 0.59. That gives you 1.17. And the error is just like a normal subtraction problem, like we talked about in the beginning of the video. Now that you've done with the subtraction problem, you can go ahead and just treat it as a normal division problem, which tells you that you have to convert everybody to a percent relative uncertainty. Then once you have that, then obviously you square those relative percent uncertainties, add them, and take the square root. That's how they got the final answer of 3%. Let's move on. Now it's time to learn the real rule of significant figures. Your book explains it as the first uncertain figure of the answer is the last significant figure. That's sort of confusing to me, so I'm going to just work out the problem with you and then sort of explain it to you how I see it. Let's say you have this problem. It's 0.002364 plus or minus that error divided by 0.02500 divided plus or minus that error. First, let's deal with the number itself, not the errors. If you were to divide that normally without any errors, each of those numbers have 4 significant figures, so your answer should then be 4 significant figures. As a matter of fact, it ends up being 0.9456. But you notice that the answer that they get is not 9456, they actually round up. They only have 3 digits, which is 946. The reason that is because the uncertainty has how many decimal places? It has 1, 2, 3, 4. So that 2 is in the 4th decimal place. That means that the answer can only go up to the 4th decimal place. And that's why the final answer only has 3 sig figs versus the 4 that you're supposed to have if you don't have any error. Your answer can't be more certain or have more digits than your uncertainty. So you have to basically take it as whatever decimal place your uncertainty is, that's how far your answer can go to. And like I said, since the 2 is in the 4th position, you can only have 4 decimal places in your final answer. Let's do a problem that deals with this. Let's try this problem, and please don't let it intimidate you. The way that I do these problems is do them without the errors, and then I figure out what I've done to get the answer. If I've added, if I've subtracted, did I divide or multiply, and then I figure out what needs to happen with the errors. Let's try it. You prepared a 0.25 molar NH3 solution, and you prepared it by diluting 8.45 mils of a 28 weight percent NH3 that has a density of 0.899 grams per mil. And you diluted it up to 500 mils. Find the uncertainty in that 0.25 molar solution. Your book does it a little different than I do. They like to break it up into parts. To me, it's a lot easier to set it up in one big equation because it lets me see exactly what I've done in the entire process. Here, I'm showing you the entire problem. Let's not worry about the errors right now. The first thing that I do is I figure out how do I have to set this problem up to get this 0.25 molar NH3, which apparently I've made. You take the density and you multiply that times the weight percent. Here, I've taken the percent off. I know that I told you that I like to keep it, but for this one, I just kept it off just to do something different. And then I went ahead and took the grams of NH3 and converted it to moles of NH3. The only thing I have left is that mils on the bottom. Well, I diluted 8.45 mils of that solution. So I'm going to go ahead and multiply that to try to get rid of my milliliters. Remember, I have to get to a molar solution. Molar is moles per liter. It tells you right there, I diluted it up to 500 mils, which is, you can convert that to 0.5 liters. And that's what I have on the bottom. As a matter of fact, I actually forgot to put the uncertainty for the 500 milliliters, but you saw there that it's plus or minus 0.2. Now, how did they get the 1.88%? Well, what have we done here? All we've done is multiplied and divide. The rule is convert everybody to a percent relative uncertainty. Now, the weight percent is given to you as 28.0 plus or minus 0.5 weight percent. But remember, I have taken away the percent. Okay, so now it's not 228, it's 0.28. So you have to accommodate your error accordingly. So that means that it's no longer 0.5 divided by 28. No, it's going to be 0.005 divided by 0.28 times 100. And that's how you get the 1.79. And then the next thing is your 500. Now remember, I've changed the decimal place. I'm not using it as 500. I'm using it as a 0.5 liters. So I switched that decimal place 3 spots. So that means I have to do the same thing to my error. What is the next thing to do? Is take them all, square them, add them up, and take the square root. And that's how they get the 1.88%. But what were we just talking about? We were talking about the real rule of significant figures. You cannot tell that rule when you do a percent relative uncertainty. So what you need to do, you need to convert it to an absolute uncertainty. So 0.0188 times 0.2498 gives you plus or minus 0.005. So your final answer, and that's why you got, if you look at the beginning, they said that you prepared a 0.250. How many sig figs does that have? That has 3. Why? Because of your absolute uncertainty goes to the third decimal place. It's plus or minus 0.005. That's in the third decimal place, so that means that your answer must go to only the third decimal place. The last thing I'm going to leave you with is this problem. It should be a lot easier than the one that we just did. To help identify an unknown mineral in your geology class, you measured its mass and volume and found them to be 4.635 plus or minus 0.002 grams and 1.13 plus or minus 0.05 mils. Find the percent relative uncertainty in the mass and in the volume. Well, that's easy. Just take your 0.002 divided by 4.635 times 100 and you get 0.043%. You do the same thing for the volume and you get 4.42%. What about B? Write the density and its uncertainty with the correct number of digits. To find the density, I take grams over the mil. So 4.635 divided by 1.13 is 4.10. Now, if we didn't have any errors associated with this, and I asked you how many sig figs should the answer have, it should have 3 sig figs total. But now that you know the real rule, what do? You take the percent relative uncertainties that you just figured out, you square them, add them up, and take the square root. You'll see that you get plus or minus 4.42%. But to find the real number of sig figs, remember, you have to convert it back to absolute uncertainty. And if you do that, you see that what you get in your calculator is 0.18122. You take that first decimal place, which is 0.1, but of course you have an 8 right next to it, so that becomes 0.2. So your final answer is going to be 4.1. you're going to remove that 0. You can only go to that first decimal place because your first decimal place in your uncertainty answer is that first digit. So 4.1 plus or minus 0.2. That is your final answer with your correct number of significant digits. That's it for this video, guys. I'll see you next time.